Hello and welcome to this next lecture on fundamentals of acoustics. Today we will derive the green function in cylindrical coordinates. The delta function, the Dirac delta function in cylindrical coordinates is given by 1 over r delta r minus r dash delta phi minus phi dash delta z minus z dash. Okay, so that now an integral over 0 to L integral over 0 to 2 pi integral over 0 to a, where this delta is contained, r dr d phi dz, that will be equal to 1. Now the PDE, okay, the acoustic wave equation, now with the delta function which is inhomogeneous, is given by 1 over r del by del r del p del r plus 1 over r square del 2p by del phi square plus del 2p by del z square plus k square p now is equal to this delta function minus 1 over r delta r minus r dash delta phi minus phi dash delta z minus z dash. One thing we need to recall here is that when we did the separation of variables, this part 1 over r del by del r of the Bessel function plus del 2, well actually 1 over r d by dr of r plus d2 by dr square r of r. Okay, this plus k square r phi minus m square by r square into r of r is equal to 0. This is what we get, where k square r phi is equal to k square minus k z square. So if r of r is the Bessel function, then this operator on the Bessel function gives this component with a negative. Just want to remember that part because we will use it. Okay. So now if the mode shape now is given by the MNQth mode shape in R, phi, z coordinates, let us say given by Jm KMNR. Okay, this Kr phi has acquired this index. Okay, this is Kr phi which has acquired the index because it is finite. So, finite cylinder. Then we have AMN P sin phi sin m phi plus AMN P cos m phi, then cos q pi z by L. Okay. If that is substituted, actually we have a summation. Okay, we have a MNQ sum on this MNQ, we have an MNQ sum. Okay. So, if we substitute this in here, okay, so what we get is this 1 over R d by dr R j m of k m n r d by dr, one more d by dr. R d dr j m. Okay. Then we have this, I will call this the phi, I will call this the phi function, sine and cosine. So, I have phi, sine and cosine, and then I have the cosine, I will call this the CQ just to shorten CQ. Okay. So, that is this part. Then I have 1 over r square d2 by d phi square of phi sc into jm of k mn mnr cq, okay, plus d2 dz square, this operates on cq, okay, into jm of k mnr into phi of sc plus k square into jm phi sc cq, that is equal to minus 1 over r delta r minus r dash delta phi minus phi dash delta z minus z dash, and there is a big sum over here, summation MNQ. Okay. So, now I will take the Q from here, this operator on Jm will give me this with a negative. So I get a sum on MNQ minus KMN square minus M square by R square into JM phi SC CQ. Okay. Now then this quantity d2 phi d phi square gives me minus M square divided by R square. So I get minus M square by R square into phi SC into JM into CQ. Okay, this is done, this is done, and this is done. Then this one, okay, this one, this gives me minus Q pi by L whole squared, again CQ JM phi SC, then plus K square JM phi SC CQ. Okay, this is equal to minus 1 over R delta R minus R dash delta phi minus phi dash delta Z minus Z dash. Okay. Now let me take this to the next page here. Okay. So if we are going to shorten this, we are going to shorten this, let's see. So this is common everywhere, this is common, this is common here, these are common because it's a mode shape, that's why it happens. So I get a summation over MNQ, and I'll put this common thing outside, so I get minus KMN square plus M square by R square minus M square by R square minus Q pi by L whole squared plus K squared into JM phi SC CQ is equal to minus 1 over R delta R minus R dash delta phi minus phi dash delta Z minus Z dash, and this goes. Okay. So what I have here is sigma M N Q K square minus K square Mn minus Q pi by L whole squared JM KMNR phi SC, I will keep it for now, cos Q pi by L into Z is equal to minus 1 over R delta R minus R dash delta phi minus phi dash Z minus Z dash. Okay. So now let's first multiply by, so we will multiply this by a different cos let us say r pi by Lz, okay, and we integrate, so we multiply that by cos q pi by Lz and cos r pi by Lz and integrate over 0 to L, okay, dz. Then this is 0 unless r and q are equal. If r and q are equal, let us call that gamma q. That constant is gamma q, it's L by 2, okay, gamma q. So I will multiply by a different r, but then r and q have to be same, okay. So we will call it, we will multiply by, therefore q itself, cos q pi by Lz, okay, dz, and integrate from 0 to L, okay. So we do the same on this side, integrate from 0 to L, multiply by cos q pi by L into z dz. That results in sigma mn, q is gone because we have selected one, the r and q have to be same, so one of them is selected. So we get k square minus k square mn minus the qth fellow has been selected by this orthogonality. This is an orthogonality condition, orthogonality, unless q and r are same, the value is 0. So we have picked the qth fellow. Then we have jm kmnr, then the phi sc into gamma q is equal to minus 1 over r delta r minus r dash delta phi minus phi dash cos q pi z dash by L. That is the shifting property of the delta function. Okay, so let me take this elsewhere. Okay, so now what we will do is this, if we open out, this is a m n q s sin m phi plus b m n q c cos m phi. Okay, so we multiply this by a sine, okay, we multiply this by a sine, we multiply the left side by a sine, okay. So summation mn k square minus k square mn minus q pi by L whole squared jm phi sc, okay, into sine, let us say s phi, okay, into gamma q into d phi, okay, and that is equal to minus 1 over r delta r minus r dash delta phi minus phi dash sin s phi cos q pi z dash by L. Okay, and then we integrate 0 to 2 pi d phi. We integrate this also 0 to 2 pi and d phi. Okay, so what does that give me? That gives me this has sin m phi and cos m phi, and this is sin s phi. For any value of s and m, this integral will go to 0. This integral will be non-zero only if m and s are equal. Okay, and so we have picked again one particular index out of the m, so we get k square minus k square, so n remains minus q pi by L whole squared j m then we have integral of sin square m phi over 0 to 2 pi, that gives me a pi over here. Okay, then I have a gamma q that is equal to minus 1 over r delta r minus r dash sin s, so s and m have to be equal, so sin m phi dash cos q pi z dash by L. That's it. Okay, that's one part. If we multiply here by cos m phi or cos s phi, okay, then we'll select the m for cos and cos here, and this integral with this will go to 0. So what we'll get here is summation again n okay. So one thing that is left is here we will have a m n q s, and here we'll have k square minus k square m n minus q pi by L whole squared, the j m with its argument a m n q cosine pi gamma q, and on this side I have minus 1 over r delta r minus r dash cos m phi dash cos q pi z dash by L. Okay, so we've taken care of sine, and cosine. Okay, now if we sum the two, that means we multiply this by sin m phi, multiply this by cos m phi, and we sum the two. Okay, so what we will get is summation n k square minus k square m n minus q pi by L whole squared j m, and here I will have this term a m n q s sin m phi plus a m n q c cos m phi, which is essentially phi SC, okay, along with pi and gamma q. On the right I will get minus 1 over r delta r minus r dash cos of m phi minus phi dash into cos q pi z dash by L. As before, the m equal to d0 term calculations will be different and only axisymmetric mode will be there corresponding to m equal to 0. I am not going to repeat the calculation, I will not make it explicit. The student should understand that and derive it separately. Okay. So, we are now left with only the n index, and in here is k mn r. So, if I take this to the next page, I take it to the next page, what I will have is okay. So, let me just say phi SC. Okay. Now I multiply pi gamma q. Now I will multiply by Jm Kmn star into r dr, and the same on this side, Jm Kmn star into r dr. Okay, and I will integrate from 0 to a. Here also I will integrate from 0 to a. Okay. So, it is an r integral. So, this comes in and here. So, what do I get? I get the orthogonality condition for the Bessel function. N index also goes now. We have k square minus k square mn minus q pi by L whole squared, and the constant from orthogonality a comma lambda mn phi sine cosine pi if m not equal to 0 and 2 pi if m equal to 0, gamma q is equal to minus Jm Kmnr dash cosine m phi minus phi dash, okay, into cosine q pi z dash by L. Okay, and here a mn q s sine m phi plus b mn q c cos m phi is given by minus j m k mn r dash cosine m phi minus phi dash cos q pi z dash by L, and b m a comma lambda mn pi or 2 pi for m equal to 0. Okay, when m goes to 0, this will be 0 and only B0 NQC will be available because cos for m0 is 1. Okay, so that calculation has to be separately noted. Gamma q k square minus k square mn minus q pi by L whole squared. Okay, in totality a summation over P M N Q R comma phi comma Z, time is separated now, is a summation over M N Q, m going from 0, J m of K M N R, then A M N P S sin m phi plus A M N P C cos m phi cos q pi Z by L. Okay, and so the final total pressure is, if we include the time also, P R phi Z comma T is equal to summation over M N Q, m going from 0 n q from 1 each, minus J m K M N R. Okay, and here for this I bring in this entity, so let us do that. Okay, let me put some brackets and this minus is repeated. Into cos q pi Z by L e to the power j omega t. Okay, so this is the response at R phi Z to a delta that is applied at R dash phi dash Z dash. Okay, so this is indeed the green function. This is the green function obtained through a modal sum. So it will satisfy all the boundary conditions. Okay, so now as I said before, in the KH integral for the interior case, okay, we have P at a certain, let us say R dash, given by an integral G del P dot n minus P del G dot n over the surface. Okay, this is a rigid walled cylinder, and therefore del P dot n on the walls is 0 and G is composed of mode functions, mode shapes which satisfy the boundary conditions, therefore del G dot n is also equal to 0. So we get a 0 here, and therefore in order to find the P, in this case let us say R phi Z, okay, we need the Kirchhoff-Helmholtz integral equation, which goes to 0, okay, plus a source term, which is G times, okay, G gives let us say R phi z and R dash phi dash z dash, okay. Then I need a Q, the source, which goes R dash phi dash z dash, d source, okay. So volume integral dv source. Okay. So if you have a source distributed in the coordinates r dash phi dash z dash, in the green function which gives a response at r phi z to a source at r dash phi dash z dash, when integrated over the volume of the source, will give the pressure at r phi zt inside the volume, inside the cylinder. Okay. If G is the sum of modes, only the volume integral over the source survives. There the surface integral is 0, as the modes satisfy the boundary condition. Else G, the capital G, can be the free space green function where all terms are present, the surface integral and the source integral, and the boundary conditions now decide which term is 0 or non-zero. For example, if walls are rigid, then del P dot n term is 0, or if walls are pressure release, then P del G dot n is 0. Okay. If neither is true, then you have a full equation, KH integral, the surface term and the boundary term, and the source term. So with this I close the lecture on interior acoustics. The thing to take away, that interior acoustics is modal. Okay, modes respond inside. Okay, so there will be highs and lows, and there will be node points in the sound field, and it is modal. Okay, and when you hit resonances, then single mode dominates. A single mode will dominate, and that is even more dramatic. It will definitely involve peaks and nodes, loud points in sound and soft points, quiet points in sound. Okay, so I close the interior acoustics portion with this. Thank you.